going on to example 4. To start this example off, really, I want you to pause the video for just a second, and I want you to try to graph this function on your own. Just do an x and y t-chart where your x values are going to be, you might try, like for x and y, you might try your x values to be 0, pi over 4, pi over 2. You can even jump to pi if you want to. 5 pi over 4, 3 pi over 2, maybe 2 pi, okay? So just maybe try graphing those points. Let's see what you get, and let's come back and compare. So pause the video, try this out, and let's come back together. Okay, so hopefully y'all got the graph and got something very similar to what I did. Just basically a curve that kind of went down through here, dropped below the x-axis for a little while, and then obviously came back up. Okay? And so that's the curve of f of x. And now from there, let's answer some of our questions. The first thing we want to do is be able to find like the local extrema where it's increasing and decreasing. We want to be able to find our critical points. So we need the derivative. So f prime of x is going to be the derivative of x over 2, which is obviously 1/2, minus 2, and then we want to take the derivative of sine of x over 2. Well, the derivative of sine of x over 2 would be cosine of x over 2 times the derivative of the angle, which is 1/2. Okay. So kind of cleaning this up, we'll get 1/2 minus 2 times the half will go away, so minus the cosine of x over 2. Okay, and then to find the potential critical point, we're going to set this equal to 0. So 0 is equal to 1/2 minus the cosine of x over 2, or the cosine of x over 2 is equal to 1/2. X over 2 is going to be the cosine inverse of 1/2. And then obviously x is going to be then 2 times the cosine inverse of 1/2. All right, now to answer that part of, okay, what are we talking about? What is x? Well, an x value of 1/2, going on the unit circle around in the full circle, to have an x value of 1/2, that means that we're looking at pi over 3. Let me put that right in there. We'll just kind of write it like this. That's going to occur at pi over 3, and then again in quadrant 4, so that'd be 5 pi over 3. Okay, so again, the cosine inverse of 1/2 could either be, that means that our angle would be pi over 3 or 5 pi over 3, but we got to multiply it by 2. So technically x could be then 2 pi over 3 or 10 pi over 3. We have to go back and check though, because it says our x values can only be found between 0 and 2 pi, and 10 pi over 3 is too large. So really, our only potential critical point is x equals 2 pi over 3. So there's our critical point for this function. Okay, now what I'm going to do is erase just a little bit of this work for a second, and we're going to go and use our sign chart because we want to test when the increasing and decreasing part. Hopefully, I guess y'all can all realize that pretty much at 2 pi over 3, we're going to be changing. So if we look on a graph, let's see, that is pi over 2, so 2 pi over 3, right about in here, we're going from decreasing to increasing. So maybe we won't necessarily have to test on our actual sign charts. We can pretty much just use the graph to show that at x equals 2 pi over 3, we can say f of x has a local min, because obviously it's a low point. Now as far as finding the local maxes, remember if we look to our graph, if we go to our endpoints here, because obviously in between the endpoints all we have is a min, but if we go to our endpoints at x equals 0 and at x equals 2 pi, what you're going to see is you actually have high points. So you can say that we have local max at x equals 0 and x equals 2 pi. So they're definitely the high points on the graph. All right, and last but not least, I guess all we have to do is just graph our derivative on there. Well, here's our derivative function, the 1/2 minus cosine of x over 2. So again, what I would just suggest to you guys is let's do the same thing. I want you guys to try to do it for a second on your own. Go to your x and y chart just like I did before, just pick some values from 0 to 2 pi. So no 0, I don't know, you can do pi over 4, pi over 2, maybe jump up to pi. It's up to you. But try to get some values all the way from 0 to 2 pi, and let's see if we get about the same graph. Okay, so to finish this up a little bit, what I did is over on the graph in purple, I went ahead and graphed the graph of the derivative. And let's see if this makes sense, okay? But remember, what the derivative should be telling you is when your graph is increasing, when your graph is decreasing. So let's look right here. The key is this point right there, okay? And I kind of, it's just a little bit of graphing error on my part, but when the derivative is below the x-axis, that says your graph should be going down. And look, they pretty much match up. And then when your derivative is above the x-axis, that means your graph should be increasing. And pretty much starting right there, that's when our graph switches over from going from decreasing to increasing. So yes, it looks like the two values actually check out, the two function values. All right, last but not least, let's finish this up. Let's do the exact same thing for this function right here. We have secant squared x minus 2 tangent x. So why don't we pause it? First of all, or here, let's find the derivative, and then what I'm going to do is I'm going to pause it and have you guys find both things. I want you to graph both the original function and then the derivative function. Okay, so f prime of x. Obviously the derivative of, you know what, I might actually write this below because looking at this initially, I'm like, we might have a lot of room involved here. Okay, so f prime of x is going to be 2 secant x, and then times the derivative of secant x, which is secant x tangent x. Okay, and then minus 2, and then times the derivative of tangent x, which is secant squared x. Okay, all right, and then combining some terms if we possibly can. Looks like we have 2 secant squared x tangent x minus 2 secant squared x. So initially, just kind of, I might just go ahead and combine this together. 2 secant squared x times tangent x minus 1. And that's the equation for our derivative. Okay, so like I said, let's pause it for a second. I want you guys to try to graph the main function and then graph the derivative. Let's try to put them both on the same graph at once, and then we're going to see if we can get the critical point from all that. Okay, well, if this problem was anything like you guys, it took me a long time to do it, and I just basically just started plugging values into my equation. I made sure I played very, very close to the tension to my domain. It's going to go from negative pi over 2 to pi over 2. And then just realizing really what I was graphing for f of x is because there's not really secant. Hopefully, most of you guys were just graphing it as 1 over cosine squared x minus 2 tangent x. And kind of the same thing there with the derivative, 2 over cosine squared x times tangent x minus 1. Okay, and then realizing obviously if you take the cosine of pi over 2, you're dividing by 0, so you should have gotten an error or basically telling you that obviously that we have asymptotes on our graph. Okay, but if we look at this, we get a general curve for our main function, and again it's decreasing all the way to this exact same point, which means our derivative should have been below the x-axis, which it was at exactly pi over 4. That was the key. There's a critical point at pi over 4. Okay, so let me go ahead and write that down. Our critical point at x equals pi over 4, because that's where we changed. Right there, the derivative was equal to 0, or right there was when we were on the x-axis. Okay, and we changed from decreasing to increasing, and right there our derivative went from below the x-axis to above the x-axis. So everywhere where the graph was increasing, my derivative is above, and everywhere my graph is decreasing, my derivative is below the x-axis. So all of this is definitely kind of playing hand in hand with each other. So to answer the last question, we might just say that there's a local min at x equals pi over 4. We don't know the endpoint, so we can't test for max or find any future max points, because obviously the graph is going to keep going up and keep going up. Just run parallel to those asymptotes. All right, let's call this lesson finished.